Hi everyone, my name is Ujjwal. Today we are going to be learning about neural networks, why they're important, what they are, and how do they work. So first, let's look at neural. Neural means neurons. So to get a deeper understanding, let's just look at an image of neuron. So what does it mean? So here, when we look at this neuron, this is basically what's present in our brain. So it takes in raw information on one end. Here it's a dendrite, and then passes it through its body, and then finally gives out different kind of information at the other end called axon terminals over here. So essentially, it takes in information from one end, does something in the middle, and gives out the information. So that's what we are also trying to replicate in terms of computer science technologies, so that we can better adapt our inputs into a particular output of our choice. So here, neurons, in another word, neural networks is basically interconnected neurons, right? So neural networks. Now let's take a basic example of how a neural network looks like. Uh, let me just assume the neuron you just saw over here as a circle, a basic circle. Then, so let me just take two neurons in this case, and assume I have an input called x1 and another input called x2. I just feed into these two neurons separately. So this neuron, let it be neuron 1, this is neuron 2. What happens? We get some kind of output y1 by processing it. Something happens inside that we are not worried about right now. Then let the x2 pass through the second neuron. Similarly, we'll get y2. Fine. This is a basic understanding of a single neuron, of how it works. Now, in order for the neurons to communicate, we'll have to interconnect them, right? That's what network means, or a neural network means. So let me just try drawing the neurons again. So let me just put one neuron for simplicity as of now. This is first neuron, second neuron, and then let this be third neuron. So I'll just connect these two neurons in this fashion. Now what happens? I just pass my x1, pass my x2 back into 1 and 2 respectively. Now somehow this information is being passed on to neuron 3 from both 1 and 2. But we just can't pass the data directly, right? Because it doesn't make much of a difference. It's directly like feeding them in raw data. We have to do some kind of weighted average or a weighted distribution of those things. So we'll assign a value for this thread. Assume each connection as a thread. I'll tell you in a while. So assume this as W1 and W2. And wherever I write W, it means weights. And I'll tell it right away. Even B stands for a bias. We'll explore these later. But for now, assume W is a particular weight given for transaction happening between 1 and 3. And W2 is also another value or a weight given for transaction happening between 2 and 3. So then, of course, this will have its own Y3 over here. That's what we are supposed to calculate now. So let's see how we can do that. Let me just move over. Yeah. So what do we know now? What's the output of the first neuron? The first neuron, let us assume it's still y1. It's going to be just x1 for now, and y2 is also going to be just x2. Cool. Then what is the input for third neuron over here? It's not simple x1 and x2 like it was before. It is basically the addition of the products. Let me explain how it works. So y3 is given by x1 w1 plus x2 w2. So it's the addition of the products. How does this work? Now assume here x1 is flowing through the first neuron. It gets multiplied with w1 and then goes to third neuron as its input. Similarly, x2 passes through the second neuron, assuming there is nothing happening inside the neuron for now. Then it passes through W2. It gets multiplied by its weight because there's a transaction weight that we have already assigned. And that W2 and X2 gets multiplied and gets sent to the third neuron. So hence both of them needs to get added, because there are two separate inputs right now. We don't have a single one. We have two inputs, which is fine. So this is how y3 is represented. So let me give you a better understanding by increasing the complexity. So let's just assume our new neural architecture is of something like this. Yeah. So this is neuron 1, 2, 3, 4, 5, and 6. Then how is it connected? Since it's a neural network, it has to be densely connected. What does it mean by densely connected? It means that one neuron is connected to every other neuron in its front. Yeah. So one is connected to 4 and one is connected to 5. When I say front, it's only in the immediate front, not all the way front. Similarly, 2 is connected to 4 and 5. 3 is connected to 4 and 5. And then, as you would know, we solved this example already. Assume this was 1, 2, and 3. How would it connect? 4 would connect to 6, 5 would connect to 6. Now, we can assign weights for this. Let's use a subscript kind of a fashion wherein, the first number represents the neuron number, the second number represents the subscript or index, for example. Like here, we can represent W1 as W11. Excuse me for that. It's not 2. It's W11. Why is it W11? Because it's the first transactional thread or a weight coming from the node 1. So W11. Similarly, this will be W12 because it's the transactional weight between the first node and the fifth node. Since it's coming out of the first node, it's 1, but it's the second one. It's just an indexing. I could have written this as 2, 1. I mean, this as the second one and this as the first one, but it's your choice. Similarly, this will be W21 because it's the second node, but the first transactional weight. And this is W22 because this is the second transactional weight from the second node. And this is W31 and this is W32. Now, similarly, this will be W41. This is coming from the fourth node. But since there's only one, we'll just follow the subscript here. We are keeping two numbers. Then here W51. Then here we'll get Y. Now assume I have three inputs, X1, X2, and X3, right? So it all goes into its respective neurons. Now, how would you represent? Okay, let me just name this as Y4 here. Y4. Whatever is the output of the fourth node, we'll name it as Y4 to go step by step, not to overwhelm ourselves. Then Y5 is the output of the fifth node. Then final Y is the output of sixth node. You can name it as Y6 if you like. So for now, let's calculate Y4. So what is Y4 going to be? Look at the inputs. Look at the inputs. It's going to be W11. I mean something with W11 because it has to get multiplied. Then something with W21 because this line is W21. It gets multiplied by something. Then the third line is W31. So something gets multiplied with W31. So it will be of something this form. So W11 into something. What is that something? In this case, it's just going to be X1 that gets sent in because we are not doing anything inside the neuron. The neuron here is not doing anything. It just passes the data as of now. So it's X1, W11 plus. So one of the input is done. Now the second input is X2 and W21. X2 and W21. And what about the third line? Third line is W31 and it gets multiplied with X3. So X3 and W31. Now similarly Y5. Y5 is going to be X1 and W12 because look, you can look at the path that's getting followed. So let's just see how it goes. So you can look at the path. X1 goes in and W12 and then it goes into 5. So that's how the path is getting followed. So you can write here X1, W12. Similarly, for fifth one, there are two other inputs. Out of 3, there are 2 more remaining. So that's going to be, what's the second input? That was the W22, but it's going to be multiplied with X2. So X2 and W22. And finally, X3 with W32. So this is Y4 and Y5. So we have the outputs that are coming out from here and here, Y4 and Y5. Now, for the inputs of 6 are something multiplied with W41 along with something multiplied with W51. But those somethings we are already calculated, Y4 and Y5. So let's just find the final Y. That's going to be whatever was Y4 here, Y4, that gets multiplied with W41 into W41 plus whatever was Y5 here, it gets multiplied with W51. So Y5, whatever was that, whatever this comes out to be is going to come here. Then that it gets multiplied with its transactional weight while the data is being passed here. So that is W51. So this is your final Y value for this neuron. So no matter what the depth of the neural network architecture here, it's always going to be calculated in this fashion. So when this happens, whatever we did here, the entire calculation, this is called as feed forward. Feed forward. What is essentially happening in feed forward? It's there in the name. You're feeding the data forward. You're going from left to right. So whatever you have data x1, x2, x3, it is getting passed into the neural network one by one. The weights, the W's basically, are getting multiplied one by one along with your inputs in some random fashion. Well, not so random in this case, it's predetermined already. And you get a final output. This is what is called as feed-forward algorithm. Now, how does it learn? Well, before moving on to how it learns, we look at another thing. Yeah, before moving on to how it learns, we'll just see how the neural network is named and how to identify certain things. I just drew a couple of round circles saying each of them is a neuron which passes in the data, but how to identify what each thing is. Now assume you have inputs. This can be any numerical data. So it goes into your neuron. And as we already saw, these neurons are connected in a dense fashion. Yes. And these neurons are also connected in dense fashion for giving you a final output Y. All right. Now, the first set of neurons in this fashion are called as input layer. This layer is called as input layer. When you're looking at from in terms of layers, this is the first layer, so we call it input layer. And the final output that you get is called as an output layer. And every other layer that you keep inside, how many other layer? You can have multiple layers with multiple number of neurons in each layer. All these layers will be termed as hidden layers. Okay. So for example, if we want to have one more architecture over here explaining the depth of the number of hidden layers that you can have, let's just assume I have 4 in my input layer. I'll write as IP for input. Then assume I have 3 as my first hidden layer. Then again 3 as my second hidden layer. Then 2 as my one more hidden layer. And finally I have 1. Well, this will be a little difficult to draw over here, although it's manageable. So it's going to be densely packed. Yes, you understand what's happening here. It's going to be densely packed here. So this is a neural network architecture consisting of 3 hidden layers, and 1 input layer and 1 output layer. This is output layer. So this is how it is all densely packed. This essentially represents the neural network in a gist. So this is how it works. And since you keep on increasing the number of hidden layers, of course, the number of weights will increase. Like here you have W1 out of 3, right? So W13, W1, you can say W11, W12, W13, and so on. So what happens is, if you increase the number of hidden layers, if the number of hidden layers increases, then number of parameters or number of weights also increases. Like the n stands for number, so number of the weights, like these are all the weights, right? That also increases linearly, or not every time linearly, sometimes even exponential as well, but it does increase. So in other words, What are we trying to understand here? Basically, the neural network architecture. How do you represent a neuron? The layers in each neuron, and what do you call them? And how this feed forward works. This is like the basic algorithm, which is very important, and how it works. So to recap once again, the data is going to be passed as if it's going through those wires, and each wire has its own transactional weight, which gets multiplied to your input, or whatever the data goes in. Not necessarily all the time it's input, because here it's not the same input x1 which is being passed here. Here it's going to be a different weight which is being passed. So yes, let's take a short break. Hey everyone. So in last class, we saw how a feed forward mechanism works. Yeah. So this time we will also incorporate something called as a bias. I mentioned the word bias last time, but we didn't really use it. So we'll just also see how a bias works and why is it needed. And at the same time, we'll see how the neural network actually learns. Because right here, the data is just getting passed into the neural network and giving us an output y. But what if this output y is wrong? What happens then? How do you make sure the neural network learns? What changes has to be made? We'll look into all those things. So for now, let's just look into the bias. So let me just redraw the same architecture. So if the input layer has 3 neurons, the first hidden layer has 2 neurons, and the final output layer has 1 neuron. And since these are interconnected, we'll have to connect each of them to its immediate neuron in the front. And let's name these neurons 1, 2, 3, 4, 5. Yes. Okay. And assume the inputs are x1, x2, x3, wherein all these values can be in any numerical number or any fashion. So let me also write another neuron called B1 and here a B2. And let me just connect B1 to 4 and 5 and B2 to 6. We'll see why did I connect it that way. So what do we know? These weights are W11, W12, W21, W22, W31, W32. It's good to practice the naming convention. And then W41 and W51. And yes. All right. So now let's go through step by step. What was Y4? I mean, the intermediary results, and this was Y5, right? So now what is Y4? Y4 is going to be X1 W11 plus X2 W21 plus X3 W31, and Y5 was X1 W12, X2 W22, and X3 W32. If you didn't understand how this works, kindly look into the previous section, which was explained in terms of how feed forward works. Now, coming back to how a bias works. Now, assume your neural network was just made up of the top half, excluding the biases. So now, how would it work, right? Uh, it would try to learn on its own, assuming there's an algorithm which makes the neural network learn. Let's just assume there's an algorithm and it learns in some fashion. But what if it doesn't learn as expected? So we need to have some kind of a bias in its decision making process, which helps it push towards the actual correct answer, or either the correct answer or the wrong answer, so that it actually starts learning. It's like you try to push someone towards their goal so that they start taking action towards it. Yes. So how does this B1 and B2 get incorporated in our equation? So in order to just incorporate, just add those B1s, add those biases at the end. Since B1 is going to the node 4, it gets added there. And similarly, B1 also goes into node 5, so it just gets added there. Now finally, the final Y, which is also same as our Y6, if you want to name it as Y or Y6, is given by Y4 into W41 plus Y5 into W51. And similarly, B2, it's adding another bias to this node by giving its own decision making process by saying you could go in this direction, or I am giving you an extra value such that you will have to learn better in order to give a better result at the end. So we just add B2 over here. So this is the final input, or I should say final output. It's going to be an input to the error deciding function, but for now let's keep it as a final output, or whatever the y is over here. So you just add the biases at the end, which just pushes the model or the architecture, the neural architecture, to giving a better result at a faster pace. Hi everyone, welcome back. Today we'll be learning about a new algorithm called as backpropagation. Till now we've been learning about an algorithm called feed forward. As we know, a feed forward algorithm is basically wherein you just pass in your inputs into your neural network and it gives an output. But what if this output is not what it's supposed to be? It's off by a lot or even by a small number. So in order to make the neural network architecture learn how to predict a better value for y, we have to do something called as backpropagation. Backpropagation is, a step wherein it involves something called as a gradient descent uh, algorithm. And when we look at gradient descent over here, what it usually means is assume this image. I'll explain it by drawing it over again. Uh, it shows some kind of value which is going downwards along the gradient line. Gradient is basically the slope of the line. So we'll just see what it actually means. Okay. Now, using the same neural network which we saw just a while ago, assume W11 is our weight of interest. We want to see how this, works or changes. By the way, before we look into W11, my general question to, sorry for that. My general question, my general question to everyone, before we look into W11, my general question to everyone is, what are the factors that can determine how a model performs? What are the factors? Does X, the values of X, like X1, 2, 3, does this determine the final output value of Y? Which will determine the value of Y? Is it X, or is it W1, 2, 3, whatever these determine? Or is it B1, 2, like the biases? Or the actual neuron nodes, like assume there's a number N, are what determines the actual value? So when you look at this, it's not going to be inputs because we can't change this. This is what we get from real world, and we are trying to make the model learn on this. And the only things that the model can change is internally, at least as of now, is it can change its weights and biases. To give a better explanation, assume this is a simple neural network here with 3 nodes, and these are the transactional weights between them, W1, W2. For maintaining simplicity, we'll just go with this. And you have X1 and X2. Okay. Now assume I give W1 as 0.2 and W2 as 0.3. So what's the value of Y? It's as simple as X1 W1 plus X2 W2, right? So what is this going to be? It's going to be 0.2 of X1 and 0.3 of X2. Okay. For simplicity, let's assume X1 is, 1 and X2 is 1. And the expected value of Y, like Y expected, is also 1 for now. So if we do the calculations, we get 0.2 plus 0.3, which is 0.5. If you check the Y predicted, like this is what is predicted, which is 0.5, and the Y expected is 1. If you see, there's a difference between these two. So in order to, make the model predict a value closer to y. Even if it's not y, we want something closer to y, like 0.998 or 0.999 to something like this. We want it to be closer to 1 at the worst scenario. Uh, so how do we do this? The only way you can see in this equation, this is what is determining the output value, right? The only thing you can change here is W1 and W2. We are neglecting bias for now. Assuming there's a bias, assume there was a bias B1 here, which is getting added. We are neglecting it for simplicity, but whatever process W or the weights go through, even the bias will also go through the same calculation being performed on it. So for now, we'll just assume W's or the weights. So now if you see here, we'll take this example and move on, move ahead with it. So if you see here, what happens, your y value is dependent on, or you can say y is a function of w's, correct? So in order to see how w1 is determining y, and at the same time how w2 is also determining y, we can plot a graph and check, right? We can see the value y, or actually in terms of y, we'll go with another expression called as an e, wherein e is nothing but an error. E is basically the error, or you can say like a cost that occurred in this case. So for this example over here, what is the cost, or like the e value? It's the absolute difference between the expected and the predicted, whatever it predicted initially. So if you take the absolute difference, it's supposed to give 1, but it gave 0.5. So the cost or the error that occurred in this case is 0.5. So we have an error of 0.5, and let's take this as W1. We'll also need to have another graph, since we're not drawing a three-dimensional graph. We'll have here W2 and we'll have here E. It gave 0.5. For what value of W1? W1 we assumed it to be 0.2, and W2 we assumed it to be 0.3. Okay, so here it is 0.2 and here it is 0.3. Now, how does W2 either increasing or decreasing it, and at the same time W1 either being increased or decreased, affect the value of E? Yes, let me reiterate. How does the value of W1 getting increased or decreased and W2 getting increased or decreased affect the overall value of E? Well, if you look at it, the expected value of E should be very close to 0. If not, in ideal case, it has to be 0. What does E0 mean? The Y expected is same as Y predicted, right? If both of these are same, then the actual cost that occurred in this case, or the error that occurred, is 0. We want this as our ideal condition, but that's unfortunately not possible in the real world. So what we are trying to find is how is W related to, or W1 and W2 related to E in this case. So we'll have to dive deep into some kind of partial differentiation here. So in order to see that, we have to see how E is dependent on W1, and at the same time how E is dependent on W2. Yes, we'll see why we are doing differentiation in a while. Now before that, if we look at the graph, or sorry, not the graph, but like the neural architecture, if you see here, let me just call the nodes as N3, N1 and N2, because we can't keep it as numbers all the time. So we'll just keep it as names, N1, N2 and N3. So now coming back to this, we'll try solving dE by dW1. How is the error that is occurring dependent on W1? Like how will my error change if I increase or decrease W1, right? But we know what's the value of E. E is basically the Y absolute difference of Y expected minus Y predicted. Yes, but we know Y expected is a constant value, correct? So Y predicted is actually what is variable in every situation, because Y predicted is nothing but what comes out of the actual architecture. What I'm trying to say is Y predicted is our actual Y that we calculate by doing the feed forward. So in other words, E is Y predicted, which is equal to Y for this example. So, and what is Y we got? Let's just scroll up and see what was our Y. X1 W1, X2 W2. And as we said, we'll ignore the bias for now. X1 W1, X2 W2. So when we do dE by dW1, what do we get? It's the partial differentiation of this function x1 w1 plus x2 w2 with respect to w1. What happens? This becomes differentiation of x1 w1 by w1 and partial differentiation of x2 w2 with w1. So the second term becomes 0 and the first term becomes just x1. So dE, or the change of error, how does the error change? Depending on w1's change is entirely dependent on your x1. So as at a magnitude of x1, not the actual value itself. Then similarly, if you do the calculations, the dE by dW2 will turn out to be x2 because the other term becomes 0 and the only remaining term just gets cancelled out and becomes x2. But what does this mean to us? How do we understand this? So every time, assume this is your neural network architecture that I'm going to draw in short. This is your neural network architecture. You pass in your x1, x2, x3 is all x's. Then you get your final y and you calculate with your actual y expected. You see the difference. If this difference is not exactly 0, you try to learn because we want to make sure it goes close to 0. Then what happens is it calculates the new values, because the only way to improve the model is by changing the values, right? Because there is no other way to improve the model as of now. We don't want to dive that deep yet. So for now, only thing we can change is weights and biases. So we are assuming the biases are also getting changed. For now, we are seeing the calculations that actually happen on the weights. Similar calculations happen on the bias as well. So when it sees the loss, it calculates the difference or the partial derivations with respect to each and every weight. Here we have 1, 2, 3, 4, 5, 6, 7, and 8. We have 8 weights here for this example. For previous example, we had 2 weights. Sorry, yeah. So we calculated the how the error changes for each weight. Like basically, when you vary W2, how does the error change? When you vary W1, how does the error change? So when you vary W1, the error changes by a magnitude of X1. Like a small difference in W1 leads to X1 change, X1 amount of change in the final E. X1 can be a value. X1, we took a value of X1 as 1. So one time the change. It's something like that if you want to understand. So how do we calculate the new weights? Because the weights has to change. Assume initially it was 0.2, right? What was W1? W1 was 0.2 and W2 was 0.3. Now, we got the y predicted, or which was actual y, as 0.5, and our y expected was 1. We saw the difference. We calculated how it changes at each and every point. So we have to change the w's now, because if we don't change it, it's going to stay the same, and we are not learning anything. We have to change something internally. So what do we do now? We say w1 new, the new value of w1 is going to be the old value of w1 minus some factor of the change in differentiation, like whatever you calculated here. So if you use this formula, w1 new is going to be, what was the old value? Old value is 0.2 minus this eta. This is a variable over here, eta. We'll see what this is. This is actually called as learning rate. We'll see what this means. We'll have to revisit that graph. And then this dE by dW1 is again x1. What was x1 in our case? X1 was 1. The example that we took right here. Where was that? Sorry. Yeah. X1 is right here. We took it as 1 over there. Okay. Now moving back, we have to see what is this eta. If you guys don't know eta, it's a Greek variable. Okay. So eta is basically the learning rate, which means if you look at this graph, this weight, like your initial weight, what does it correspond to in our terminology? It is our old weight or initial weight. How does it change? How we know how it changes now, but how much should it change, right? How much should it change? It's showing the arrow marks here. It is going to a point where the cost, you can see the y-axis is cost is nothing but the error, and x-axis is the weight. In this case, assume weight is x-axis is w1, the cost is e. We need the e value to go to 0, or at least go towards 0. So in order to go towards 0, we have to go down, but in what steps? These incremental steps should be huge or small. That is determined by this variable eta. So now if eta is too big, of a value, then the incremental steps that the value takes is also large. In that case, what happens is, let me just draw that graph. Assume this is our graph, and your initial weight value is here, and this is w, and this is our e. Now it has to go down. Now if your eta value is too huge, then you'll miss that value and go all the way across to the other end of the graph, increasing the loss value again. Of course, you would have changed your value. Initially, your w value was 0.2. Assume this is 0.2, and you would have changed your value to 0.1. But at what cost? You changed your you increased your error again, or kind of stayed the same. You didn't really improve your model. So you have to take small steps, or very small steps, until you reach to this point. Assume the value is turned out to be 0.15, at which point your error turns out to be close to 0.01, something like that. So you have to take smaller steps. So this eta is also another learning parameter which the model will try to learn, or you can also set it manually, such that it takes incremental steps and reaches to a point where the weight also changes, such that the loss value is at its minimum, the lowest that it can reach. At further point, it can't learn anymore. That's a different issue. We'll look at what it can be done. So for now, let's assume eta value is, what will be the w1 new is equal to 0.2 minus something into 1. Let's assume eta is equal to 0.01. So 0.01. So this is going to be 0.2 minus 0.01. So if we subtract, what's it going to be? It's going to be 0.18, right? 0.18. Yeah. So what does it say now? So initially we had w1, I'll write it as old. Initially it was 0.2. Now if we take w1 new, it is going to be 0.18. And similarly, if you calculate w2 old, we took it as 0.3, and w2 new will come out to be some other value that you can do the calculation. So next time, in the next iteration, when you calculate the new y, the new expected value of y, it's going to be w1, but this time you have to use the new value, w1 x1, plus similarly w2 also you have to use the new value, x2, and that bias we are not dealing with it for now, so you can ignore it. So if you do this, you will get your new expected value, and you have the same sorry, this is not expected, sorry for that, it's the new predicted value, and your expected value stays the same. You can compare the difference between these two. This time the loss or the error would have gone down. Instead of 0.5 as the loss, maybe it would have gone to 0.48 or 0.49. This would be your new loss. It's an improvement, right? Initially the loss was a bit higher, this time it reduced. So by doing this operation, by calculating dE by d with w1, w2, with all the w's one by one, you change the w values. All the w's have been changed by, let's assume 30th step. This was one step, whatever we did here. It initially you calculate. Okay, let's just summarize it. You take your x's, pass into your model M or the neural network architecture, get your first set of y's with all the w's. Then based on this y, you calculate the error and then get the new w's. Then using these new w's, these new w's get updated here. Then you pass in your x into the new w's, get a new y with the new w's, and then calculate the error again. Keep doing this again and again until your error becomes close to 0, or it becomes plateaued at one point. At that point, it doesn't learn much from there. So that's a different issue. We'll look into it later. So what basically is happening is, it's a loop wherein it iterates again and again, and each iteration is termed as an epoch. in simplest level. At the lowest level, it's called as an epoch, or you can call it as iteration for now if you don't want to complicate things. So this is how it works. Feed forward. So the entire working of a neural network is basically feed forward. So wherein you just multiply and add all the terminologies, plus you back propagate. What happens in back propagate? It defines the differentiation, then calculates, I mean, first calculates the error, then calculates the partial differentiation for each weights. How does varying small weights differ the error? If it's helping towards it, then it will do its thing. That's the whole point of calculating the differentiation. So it calculates those weights, then changes the value of the existing weights, like replaces or updates those, such that in the next iteration, the error is less. If it's not less, then it will take its next steps to go in the other direction and improve it further on. So this is the complete working of neural network at the lowest level. We'll look into convolutional neural network and other kinds of neural network later on through code as well, but mostly in code. But for now, I think this should be a very good understanding of neural network. That's about it. Thank you very much.